So we're all aware of the Cambrian explosion, this probably the most remarkable event in the fossil record. And it's an event that we know had profound biological changes, but it was also a time of big transitions in Earth's physical environment. Cambrian has usually been considered one of Earth's greenhouse climate intervals, but getting any more specific than this has been very difficult because of a lack of available data and methods to analyse the data that are available. So we want to try and refine this and improve this environmental picture of the Cambrian radiation. Where to begin? We've decided to approach this from a number of angles, incorporating quantitative paleoclimate data, lithological data, and also climate modelling, and this is where I will begin with us now. So we use the FAST ocean atmosphere model, which is a coupled ocean atmosphere model, general circulation model. It's not one of the most complicated models available, but it's good at giving global and regional climate picture. And it's been successfully applied in the Paleozoic to tackle other questions about unresolved Paleozoic climate issues. To construct a climate model, you need a paleocontinental reconstruction and a base map. We decided that we would focus on one of the most widely used paleocontinental reconstructions, the Torsvik and Cox suite of models, variously 2009, 2013, and most recently 2016. And over this, we need to overlay a paleotopography and paleobathymetry. So this model, this paleocontinental reconstruction, is made on the basis of paleomagnetic and biogeographic data, and we overlay onto that. We there? Good. We overlay onto that published lithological data that gives some indication of altitude or water depth at any particular location. This is, by necessity, a fairly crude map, but it gives the right picture. So this is our land mask. We then need to specify some orbital parameters. Since we really don't know what these are in the Cambrian period, we investigated a range from present-day conditions, also orbital conditions that would give a warm northern hemisphere or a warm southern hemisphere, and a few others as well. And finally, we need to specify the carbon dioxide levels, or the greenhouse gas forcing of the early Cambrian world. This is something that has been done in a number of ways, has been modelled in a number of ways before, and we're taking, again, a range of values to encompass the potential range. We're looking at 16, 32, and 64 times pre-industrial atmospheric levels. For those of you who know of it, the Berner geocarb self model predicts somewhere in the region of about 30 PAL for the early Cambrian. So we are now ready to run our climate simulations for the early Cambrian period, and it will come as no surprise that it does actually come out as a greenhouse environment with a relatively shallow latitudinal temperature gradient. And as we crank up through 16, 32 and 64 times present atmospheric oxygen levels, the temperatures globally increase. The latitudinal temperature gradient doesn't change all that much, but what's important is that we do end up with temperatures that are in the feasible range for early Cambrian, for life across the range of latitudes. So how do we work out which is the most appropriate level to go at? How do we choose the most appropriate greenhouse gas level here? Well, we can look at the latitudinal variation of each model, and we can see that although precipitation doesn't seem to change very much, there is a range of temperatures between the different models. And we have here the lowest line is 16 times present atmospheric oxygen. The highest line is red one, is 64 times, and this suite in the middle are all at 32 with different orbital forcings. What this means is the greenhouse gas level does make a difference, but the orbital forcing, at least on the scales that we're modelling, doesn't. So we can focus on the greenhouse gas level for calibrating the model. Can we calibrate the model? That is the real question here. For those of you who were in Lyon last year, you may recall my talk on using oxygen isotope data from phosphatic Cambrian microfossils to work out early Cambrian temperatures. Here we use those temperatures for Avalonia, about 20 to 25 degrees Celsius at about 65 degrees south. And we find that whilst 64 is a bit too warm and 16 is a bit too cold, 32 times present atmospheric oxygen just about fits the bill with a about 20 degrees Celsius predicted from the model at the point of our data collection. So these are then the first calibrated general circulation models for the Cambrian period. What can we do with this? No matter how good our isotope data coverage gets, because we are in such deep time, we're never going to have global coverage. So can we use these models to extrapolate out and say something more broadly about global climates during the early Cambrian? Well, the Köppen-Geiger climate classification scheme is one of the most widely used in the modern world, and it has 5 main climate regimes, and these are determined, as are the sub-regimes, by temperature and precipitation data. This is stuff that we can pull out of the climate model, and so we can construct our own climate zone maps for the early Cambrian from our models. And in doing so, we find that we have quite widespread arid and semi-arid settings. We have a monsoonal band in the middle and around the equator, and we do get down to some quite cold temperatures and cold climate regimes in the southern hemisphere. Great, but can we do anything more with this? This is still modelling and speculation. So it's been suggested, and lithological data have long been used for understanding environmental conditions in the past. And a recent compilation by Bucco et al., this Atlas of Lithological Indicators of Paleoclimate, started to pull together a compilation of these data, these geological data that can be indicative of the climate regime of a particular location at a particular time. So we've taken the Cambrian part of this database, expanded it, improved it a bit, and improved the time constraints on quite a lot of it. And we find that, as you would expect, there are a range of lithologies that generally represent greenhouse conditions spread over a wide range of paleolatitudes under these Tors, Big and Cox reconstructions. But there are some notable oddities. For instance, we have very high latitude Oolitic limestone, bauxite laterite deposits, and evaporites as well. Next to these are some dropstone, tillite, and other glaciogenic deposits, though these aren't so well constrained in time. They do occur in probably early Cambrian rocks here. So this needs some more rigorous testing. To do this, we selected a suite of geological indicators of paleoclimate. We looked at the range of climatic conditions and regimes that they could fall under. And using this, we also applied a weighting as to how confident we were that that would indicate the climates that we thought that it would. When we go back to our climate zone maps, we find that there's generally quite good agreement, but there are a couple of areas that stand out, notably those North African deposits that I told you about just a few moments ago. So these have been noted before, and it's led to very, very disparate paleogeographic reconstructions. Note that both of these were published in 2013. This one's obviously got a wider range of publication dates as well. So do we need to have such a fundamental rethink of early Cambrian paleogeography to account for these high latitude deposits? Well, probably not. A whole suite of Cambrian paleocontinental reconstructions have been put together by a whole suite of different authors. And here we take an example from Alvaro et al. In 2013, in which they base it on trilobite biogeographies in particular. And under such a model, they suggest that North Africa was, rather than sitting across the South Pole, was in fact 30 or so degrees further north. And when we look at this in our climate zone maps, we find that it puts us right into this sort of humid equatorial region. So such a relatively small rotation of Gondwana could account for these, rather than a fundamental rethink of Cambrian paleocontinental reconstructions. And with that, if we can get there we go. So we present here the first calibrated general circulation models for the early Cambrian period. These generally support a low latitudinal temperature gradient and a greenhouse climate, and we think that with these new GCMs, we can start to interrogate Cambrian and potentially earlier climates where there is a lack of data or it's been very difficult to analyse the available data. Thank you.